Hi friends, so today we begin lecture 17 in our course and today I'm going to talk about the important problem of flow separation. I'm Dr. Ranjan Ganguly. Now let us start with flow around an airfoil. So essentially you have an airfoil section and this section is at a very low angle with respect to the airflow. So what you get is essentially attached flow. And so the flow takes place like I have drawn here. All the streamlines are very smooth. They are all very close to the airfoil and so there is no flow separation taking place here. And in this kind of situation, skin friction drag will dominate and it is essentially mostly laminar flow taking place here. Now, if we were to look at the pressure distribution in this kind of flow, we are going to get something like this here. So you essentially have Cp. Remember in our last class, we defined Cp as a non-dimensional way of writing pressure. So essentially it is essentially pressure, but it's non-dimensionalized in this form here. And so Cp varies from 1 here and it goes down and then it goes up again. Now this region here where dP by dx is positive is known as the pressure gradient and this is the region of the adverse pressure gradient. But we can see here for attached flow that this adverse pressure gradient is relatively mild and so the flow is going to stick to the surface and essentially we are going to get good flow characteristics. Now this diagram I have drawn here is of course of pressure on the top surface of the airfoil section. Now next let's consider separated flow situation. So here we have the airfoil section and now the angle with respect to the flow is much larger. So what has happened is that the flow takes place in this manner and you also get some separation which is taking place near the trailing edge region. So essentially the flow detaches at some point here at the trailing edge and then you get these complex flow patterns and you can even have a reversal of the flow situation here. So this kind of flow is known as separated flow and in this kind of flow pressure drag will typically dominate. If we now go ahead and look at the Cp distribution on this separated flow airfoil, we are going to get a graph in this form. So essentially you have the chord length here and you have Cp going all the way down here to some pretty low value and then again coming up in this manner and you can see in this location that there is a severe or strong adverse pressure gradient dP by dx and so correspondingly we are going to see there is going to be a loss of lift and there is going to be an increase in drag. Both these are very negative because loss of lift means that you have less payload carrying capacity and increase in drag means that you now require more power as far as the engines are concerned or as far as your propulsion is concerned. So these are things you need to design for whenever you are designing the flight vehicle. So let us look at the pressure distribution on the airfoil in these two type of conditions. So what happens is that the bottom pressure does not change, but what changes is the pressure on top of the airfoil or on the top surface of the airfoil. So in red, I have drawn here the pressure corresponding to the attached flow situation and in the green I have the situation here for the separated flow. Now you can clearly see that when the flow is separated there is a tendency towards the trailing edge as far as the forces and the pressures are concerned. So what happens is that the attached flow situation has a higher lift and a lower drag, but the separated flow situation has a lower lift and a higher drag. And this is basically caused by the kind of pressure distribution which you are getting because of the separated flow situation. Now, both these things are actually deleterious as far as any flight vehicle is concerned. You are getting loss of lift, increase in drag, none of which you may actually like in any situation. So these are the negative effects you get because of flow separation. So let's now think about the physics as to why would flow separate. So we already pointed out the adverse pressure gradient, that is dP by dx greater than 0, which we saw in some of the graphs before. And what this adverse pressure gradient does is that it slows down the fluid. So essentially the fluid velocity will decrease as the pressure increases. Now, of course, the fluid would slow down both inside the boundary layer and outside the boundary layer. But what happens is that outside the boundary layer, the velocity of the fluid is typically quite high, and therefore the slowdown doesn't matter much. But when you are inside the boundary layer, like in this situation here, you already see that the velocities are quite less. So this is the velocity with respect to the thickness side of the boundary layer. And you will see whether you are in laminar or turbulent boundary layer, the velocity in this region is relatively less. And because of this adverse pressure gradient, this is going to become even lower. And so what will happen is that at a certain point, this flow near the surface or at the surface is going to come to a stop and effectively reverse direction, and so you are going to get flow separation. So flow separation is intimately tied to what happens inside the boundary layer, and the fact that at the wall of the boundary layer or at the surface of the body the velocity is very small, and that is something which plays an important role as far as flow separation is concerned. Now, of course, we can immediately realize that the effect is going to be different for the turbulent boundary layer compared to the laminar boundary layer. For example, if we consider the turbulent boundary layer, this is going to have a relatively higher velocity near the surface. So I have drawn that in the blue line here, and you can see the velocity is going to be more near the surface. So what this means is that the flow is going to reduce less, or the flow speed is going to reduce less, and the flow is therefore robust to separation. So this is a somewhat counterintuitive concept which we learned from here, is that turbulent boundary layer actually is robust to flow separation. In contrast, what happens in the laminar boundary layer is that you have a lower velocity near surface, and therefore what's going to take place is that your velocity is going to further reduce, and so you are going to reach that zero velocity point and the flow reversal more quickly. So actually the laminar boundary layer is very sensitive, and therefore if you have any kind of pressure gradient, it is likely to separate here. Now in a previous lecture I showed different pressure distributions and how you can actually tailor the pressure distribution so that you can hold laminar flow for a longer time for a given airfoil section. And so if you want to look at that, go to the previous lecture and then take a look at those type of airfoil section which essentially have the highest thickness somewhere near the mid chord region. Now let's look at the effect of skin friction drag because of these two type of boundary layers. So again, recall that the skin friction drag is dependent on dv by dy at the surface, that is at y equal to 0, that is at this point here. Okay, so the skin friction drag due to shear stress on the boundary layer wall will clearly be less for laminar because this slope is less, and it's going to be more for turbulent because the slope here is more. So clearly we will see that because of this dv by dy slope being more for turbulent, the skin friction drag is going to be more for turbulent flow. Now we also see that pressure drag is going to be impacted differently here. So we'll see that the pressure drag is going to be actually more for laminar flow and less for turbulent flow. Pressure drag is also sometimes known as form drag, and the total drag is actually the skin friction drag and the pressure drag. So we combine these two to form the complete drag here. Now this is sometimes also known as the profile drag. Now keep in mind that this drag is coming because of the profile or shape of the airfoil section. There is another type of drag known as induced drag, which actually takes place because we are trying to generate lift. That is something we will discuss later in the class. But as of now, we have two types of drag, which are skin friction drag and pressure drag. So to summarize, we see that flow separation takes place primarily due to adverse pressure gradient, which acts on the airfoil section upper surface, and therefore we see that boundary layer plays a key role in flow separation. So we also saw that when we have laminar flow, we get low skin friction and high pressure drag, and when we have turbulent flow, we have high skin friction and low pressure drag. So These are kind of interesting situations which take place here, and depending on the type of flow you are going to get, the type of drag which you are going to get is going to be different. So pressure drag is also known as form drag, and the total drag would be skin friction drag plus pressure drag. Total drag is also sometimes known as profile drag. Now the choice of airfoil section for design would involve a trade-off between these two type of flows, laminar and turbulent, and these two type of drags. So we cannot really say that laminar flow is always good and turbulent flow is always bad, because as we saw, the turbulent flow can actually be good sometime for flow separation. It can retard flow separation. So actually turbulent flow is more robust to flow separation, and laminar flow may actually be more prone to flow separation. So these are certain things we need to keep in mind based on the design we are doing. And in many cases, actually, a turbulent flow situation may be preferred, because anyway we know that the flow is likely to separate. So the turbulent flow is going to be more robust to flow separation in those cases. So this was my video for today, and we clearly got introduced to certain important concepts about skin friction drag, about pressure drag, about profile drag, about form drag, and also we found that, in contrast to what many people may think, turbulent boundary layer may actually be better in terms of flow separation in many cases, because turbulent boundary layer is more robust, and therefore that's something to keep in mind whenever we are thinking of boundary layers and so on. So I'll end this video now, and I will see you in a lecture sometime soon. See you then.